Okay, so now let us take a look at what we call the limit comparison test. Okay, limit comparison test, it says like into this. We have two series. They're nth term, a and b, and they're both positive for all the n's, which is greater than capital N. Capital N is an integer. And the limit comparison test, it says like this. If limit as n goes to infinity, an over bn equals c, for sure c is going to be some constant if it exists. Then series an and series bn, they either both converge or both diverge. Okay. So that's the first case for the limit comparison test. And so the second situation is, okay, if limit an over bn equals 0, and meanwhile, the series bn, which is the series in the denominator, converges, then we can also get the conclusion that series an is also converges. Okay. So this limit part, it actually give you the idea is, if bn is already converging and this limit is also equal to 0, it's impossible for this series an to be diverged, okay? Because if it's diverged, this limit might not be 0, okay? And the last case is if limit an over bn equals infinity, and this situation is if bn diverges, and then the an also diverges. Okay, so that's the what we call the limit comparison test. Okay, and so excuse me. So for this part, let us first take a couple of examples here. So first of all, let me look at here. Look at this problem here. We have 3 over 4 plus 5 over 9, and then plus 17 plus 7 over 16, and then plus 9 over 25. Okay, and the question asks us, okay, if this series is converged or diverged. Okay, so that's our first example. And we're going to try to use the limit comparison test to handle this problem. But before we apply that, first of all, we need to find the sigma notation for this series. In other words, I need to write what is an, which is the nth term expression in terms of n, and then I can move forward. Okay. So the question here is, okay, how do I figure out this an? It turns out that the denominator is not that bad. It's 2 squared, 3 squared, 4 squared, and 5 squared. Okay, so if we count n starting from 1, as you can see that for here it's going to be 1 plus 1 squared. This is 2 plus 1 squared. This is 3 plus 1 squared. This is 4 plus 1 squared, which the denominator is going to be n plus 1 squared. Okay. So for here, this an, we can know that the denominator is going to be n plus 1 squared. And on the numerator, it's a 3. Excuse me. It's a 3, 5, 7, 9. As you can see that, it's all odd numbers. Okay. As we recall, let me grab a tissue. So as we recall that all the odd numbers we can actually write into a 2 times n plus some odd starting numbers, right? So in this situation, the format is going to be 2n plus 1. Okay, 2n plus 1. So turns out this is going to be the general expression for our an. Okay, and of course, this is a series we are looking at. Okay, in other words, starting from now, we're going to focus on this problem. Okay, so, and then after that, let me move a little bit more here. So as you can see, for here, if I expanded that, so the top is 2n plus 1, the bottom is n squared plus 2n plus 1. So the idea is, if we only look at this expression here, as n is become extremely large, it turns out that this expression is going to behave very, very close to this. It's almost identical, right? As n goes to infinity, because this one can be ignored compared to this 2n. Think about this n become, let's say, 10 billion, right? And then on the bottom, n squared is going to be the dominating term. So as n goes to infinity, my original series kind of behaves almost identical to this series, okay? And if we simplify this, 2n over n squared, turns out that this is the series I have, which is series 2 over n. And if I factor this 2 out, so I'm going to have 2 times this sigma notation y over n. Turns out this is a harmonic series, okay? And we know that harmonic series is divergent, okay? Is divergent. So we know this is a harmonic series. And so you can see that right now, my original series here, I can denote this as an. The comparison series, I can denote as bn. So keep in mind that I just verified that limit an over bn, which is the an over bn, as we take this limit, which is 2n plus 1 over n squared plus 2n plus 1 over 2 over n. And then it equals to multiply the reciprocal of it. It's times n over 2. Turns out this limit becomes 1, okay? And then that actually satisfies, remember, the limit comparison test. We have a and bn both positive, sure. And then a limit as n goes to infinity, a over bn equals, in our problem, equals 1. Then an and bn, they both either converge or both diverge. And we already know that our bn, which is a 2 times a harmonic series, it's still diverge. So based on the limit comparison test, we get as a conclusion that my original series, which is 2n plus 1 over n plus 1 squared, this series diverges, okay? So that is the first example for the limit comparing test.